Um, so just a quick overview. Let's just say. So hopefully the stream works. Okay, so as you come into Canvas, this is the first thing you should see. And just as we're keeping track, this first block, I'm gonna have the copies of the recorded class, and the attendance quizzes should be right underneath them. So there'll be a class recording that was from Tuesday, the attendance quiz for Tuesday, and then probably it'll be tomorrow morning. It might, I'll put today's class recording with today's quiz there, and it'll be there. What I want to show you is what I put with the class recording. I can click on it. Oh, I gotta be over here. Yeah, there we go, that's better. So with the class recordings, there's the video, and then right underneath are class notes. So what I do is as I sort of, each time I make a new screen, it saves the old one, and it makes a PDF file. I'll go ahead and open it up. Let's see here in a moment. There it is. And it kind of records what was on the screen. So there's like 20 pages of notes. So it's another way to look at it. Those are all in the video as well, but here these are just page shots. So sometimes they might be more helpful if you're just looking for something, especially if you go to the first one or close to the first one. You might find something, and sometimes there's a blank page in there, but you know, if you're looking for the word of the day, it's a quick way to find the word of the day. Those are there. So those are kind of the resources that are available. Let's see, here we go. So I'll take that down. The other thing I'm hoping you will test, and I'm glad somebody let me know they were testing it today, because I actually didn't make it available. Here we go. You'll see there's an unnamed quiz showing up now. I just put it there before class. That is a one-question quiz to test out the exam system I'm going to be using, which is Respondus Lockdown Browser. So as you go through it, it'll take you through checking your webcam. You take a picture of yourself, you show an ID, you show your area, and it records all that kind of stuff. And then when you're taking your test, it just records. And again, it gives you instruction while you're taking an actual test if you need to go use the restroom or get called away for some boiling milk or something on the stove. I don't know. Just let me know, hey, emergency, I'll be right back, and then come back. I'll be honest with you, I don't know what those videos look like, and I'm not going to sit down and watch 30 videos of people taking tests all day, but it's recorded, so that's the idea, is that you know it's recorded, I know it's recorded, so if there's any issues we can take a look at it, but probably we're not going to go spend our evenings looking at videos of people taking tests. But that's how we can do a proctored exam. If you have difficulties or it doesn't work to you, we'll make alternates, maybe using the testing center or something else, but I think this is a nice option so that you can take it at your leisure anytime you want. Maybe you think best at 2 in the morning or something and you want to take it then, great. Or 2 in the afternoon, whatever works best for you, you do it. And I'll give you, once we do have it open, the actual test, there'll be a time period. I'll say, you know, it's open now, please try to get it done within a week. And then again, remember, there's always a retest if you don't do as well as you want. But I want you to be prepared. I want you to do the best you can the first time, hopefully doing well. But if not, we'll take a look at what you did. You can review and hopefully retake it again. So working sort of towards a mastery approach. Okay, and I think those two things will have none of us worrying about cheating. We'll just focus on learning the material and we're fine. I think that's it. Any other questions? Okay. I've had a few issues come up with due dates, and this is one of the reasons I usually don't like using due dates. It's a new program, so I'm thinking what I'm going to do is I'm going to take the actual due dates and put them like all at the end of the class. So that means that it's now your responsibility to keep yourself on track, because the quizzes, everything will still be due. But then it won't stop you from working on something that maybe you were a little bit behind on or didn't understand it at the beginning. And sometimes this class is it. After we get done tonight, you might have been struggling with like the first couple that we did, and maybe tonight we'll unlock that, because actually that's tonight we're going to bring everything together. Limits, continuity, and an algebraic approach, a numeric approach. We're doing it all and in a way that hopefully makes it make sense. Okay, so we'll keep going with that sense. Oh, one more thing. Also, I do grade updates. What I do is I take WebAssign, I download the entire grade book into an Excel spreadsheet. I transfer those scores. I do a little bit of math on them because I make each one worth 20 points. So if you got 100%, I turn it to percent, you get full 20 points. Let's say you were working on one and you only had 80%, but next week you go back and review the ones you missed, and now you've got 100%. That next spreadsheet I do will pick that up. It will pick up the higher score, multiply it, and give you the full 20 points. But it'll be like a weekend thing I do. So I don't do it every day. I don't do it 2 or 3 times a week. It's not that long of a process, but it's not a lot of fun. So I do it about every weekend. Okay, so you'll see. So if you're not quite on schedule with what's going on, don't worry. You'll see some zeros if you hadn't, like you completely didn't get assignment, and I said we probably should have been done by then. I do put in zeros just to let people know that they should get onto it. But once you have it completed, those zeros will get replaced by whatever you did. Full points if you got 100% on it. Okay? Good. So, we ready to begin? Or I lulled you all to sleep already.
It's a quiet class.
That's a quiet class. It's an evening class. Stress from the commute, everything. So, okay, I understand. Okay, so let's go ahead. Choose a word of the day. Who hasn't chosen a word that's got something good for us? Something inspirational.
Inspiration.
Inspiration is a great inspiration. Okay, very good. Awesome. So we'll go with inspiration. Inspiration. Okay. Wasn't that the song that McFly was singing back in the Back to the Future movie? Anyone remember that one? You are my inspiration. So, I don't know. Maybe too old. Okay. So tonight we're going to first take a look at 10.5, which are numerical and graphical looks at derivatives. And again, this is going to sort of dovetail or go in with what we were working on when we were looking numerically at limits and graphically at limits. The thing that's going to change is instead of looking at a limit as we get close to a point, we're changing it a bit. We're getting closer to that point, but we're taking a second point and we're making that second point get closer to that first point. So that gives us and so we're not looking at y values anymore. What is the output value of the function? We're actually looking at what is the slope of the line between those 2 points. So that's all that's different. It's really the same lesson pretty much as what we were doing in 10.1 and 10.2 and I think probably 10.3 on limits, except now we're throwing in this calculation of slope. Okay, so the first thing I want to look at is a little bit of review from the last section on average rate of change. so if we have 2 points, right, we have like x2, y2, and we've got an x1, y1, so 2 points. We label them this way because, well, x1 is just the first x value, and y1 is the first y value. And they're just arbitrary. Those little, what do they call them? Sub points. These little 1s and 2s. They're arbitrary. I could call them either way. So it doesn't matter really which one I put on top or which one I put on bottom. Okay. And the way I've been showing you primarily is how to take a slope is we take the top minus the bottom. So I'm going to do it with this abstraction. We've been doing it with numbers so that we didn't have to have the formula. I'm just going to show you that what we've been doing also leads us to this formula, the slope formula. Okay, so when we subtract x2 from x1, what do we get? 2 minus x1. Because they're actually different variables. They're both x variables, but one is an x1 and one's an x2, so they could very well be different. Okay, and then what do I get when I subtract the y's? I get y2 minus y1. Wow, that's cool. You ever see that before? And then what have we been doing? Well, we've been taking the x value, and again, in our case, we were using numbers. This became a number. We tucked it underneath the y number, and we got a fraction, which we call the slope, the average rate of change, which is exactly what every algebra book has taught us how to do, and they call this m, right? Most places. They call that the slope. We call it the average rate of change when it's on some other function, and we're just getting when it's not necessarily a linear function. We call it slope when it's linear. We call it average rate of change when it is sort of just on any particular function, and we're just taking two points. Okay, and this is the basis for everything we're going to do tonight, really. So you're going to do this calculation again and again and again. But I'm also going to show you when we talk about the derivative, that's where the derivative comes from. But the book shows you a formula. They leave out a step. And I'll tell you what, that step is what caused me to, I didn't fail it, but I got a C. And if you're a math major, getting a C in a calculus class is about the same thing as failing it. So I had to take it again. Actually, I took both derivative calculus and integral calculus twice. I got C's on both of them the first time, and that was the second time that I started to realize, because that teacher showed me the one step that all the books leave out, and you think the derivative is some sort of magical thing. But I'm going to show you today that that derivative is just the slope. And I'm going to show you the missing step, and you're going to see that you'll probably get to the point where you leave that step out too, but knowing that that was what was happening, the mystery will be solved for you, hopefully. Okay, so what they do for the limit, and I'm going to start with the way I would look at it. So the process of getting a derivative is we really start with this, an average rate of change of 2 points. But conceptually what they're going to do is they're going to call one of the points, they're going to set one point, and then what they're going to do is the second point happens by adding some value, h, okay? And h was what we're going to change the distance between the 2 points is how we do this, okay? So let me see if this is a good place to start or not. So the definition of a derivative is going to be, we're going to take this formula, we're going to take this y value. So this is our sort of our second point. I guess maybe, let's see, our 2 points are now not going to be x1, y1. They are going to be, they're going to be a plus h, comma, f of a plus h. That'll be one of our points. And then the second point will be a little simpler. It'll just be a f of a. Because f of a is just a y value, right? So now these are 2 points. We've got an x value and a y value. So this is where we're going to start for the derivative, building off of what we did up here. Okay. And so using this formula, we'll take the y2 minus the y1. So notice I'm taking the y values, putting them up in the formula. What do I put in the bottom? Very good. The first one is a plus h. And the second, I'm subtracting the second x, right? I'm subtracting a. This is the part that they don't include. They just jump to, and you'll see why maybe they don't. And then what we're going to do is this is 2 points. This is what we call a secant line. It's a slope of a secant line. But to get the derivative, which is going to be instantaneous change, so it'll be slope at a point, what we need to do, we need to make that h get down to 0, because h is just what we're adding on to it. So that's where the limit comes in. We really didn't need the limit for much of anything else except for this. So we spent a whole day or whole section talking about limits, and what we're going to do is we're going to let h, which is the distance between a and the next point, we're going to let that go to 0. Okay. So this is the one point that I've never seen this particular formula in any book. What they do is they simplify this, and that's what you'll see in the book, and that's where the mystery came up, at least for me. So how can we do anything with the top part of this statement? Just say no. You can't. Doesn't look like it, but you're trying to think. Yeah. So because we don't have a function yet, so we actually can't do anything with it. It's just symbols right now. It's one y point minus another y point, but there's nothing we can do. Here the same thing. It's an x point and an x point, but look at one x point is actually just a plus h. It's not inside of parentheses or anything. And then we've got a minus a. Do we have some like terms here? We do. The two a's are actually the same value. So there's a positive a and a negative a, and we can combine those into 0. That's the magic of this whole thing. This is what you see in a book, is they take this step, they take away the a's, they combine the a's, and they never tell you what they did. They just say, oh, this is the difference formula, and this is what you'll see in our book. The limit as h goes to 0 of f of a plus h minus f of a. Okay, nothing we can do there. But in the bottom, they just have an h. I'll tell you, I don't know. You guys are probably sharper than I am, but this is what blew my mind and got me always behind. I just couldn't understand that was slope, because the bottom didn't look like slope. You need to have 2 x values. You need to subtract 2 x values. Well, they did it. They just never told me. Ever feel like that? You got left out. Everyone else was enjoying the party, but you didn't even know what was going on. That was me. Okay, so this is what you're going to see in our book. This is what it means. It's just the slope that we've been working with, but now we're going to let h go to 0. Incidentally, can we let h go to 0 in that formula? No, because we can't just plug in 0, because that would give us a division by 0, and there's problems. So what we're working on tonight now is we're going to start with that formula. We're going to look at it numerically, we're going to look at it graphically, and then in 10.6 we're going to algebraically do some work which will involve some factoring that we basically get the h out of the bottom. And if we have some nice stuff to work with, we can do it. And so what we do is we build a pattern of what's going to happen, that it actually works with stuff that's not too difficult to work with, so that we can apply it next week in Chapter 11 to a technique that is a lot easier to do. So when we get some things like x cubed, or x to the 4th, or x to the 27th, it's going to be an easy thing for us to do. but algebraically using limits is very, very cumbersome and would not work for most problems. Yes?
So would a plus h be, is that y1?
A plus h, this one,
Yeah.
that would be x, actually that would be x2 up in this example because I put it on top. But it could be either x1 or x2, right? It's one of the x values. The f of a plus h is the y value of that point. So what you see is you've got an x value and a y value. So now you can see the 2 points are there. It's just that when it simplifies, it doesn't look like you're dealing with 2 points anymore. And again, when I was going to school, I was back in the 80s, so that was too many years ago, right? Probably longer than most of you are alive. Anyone born before 1990? Oh boy, now I really feel old. Okay, so anyway, ancient history, right? Yes, sir.
So you have y2 minus y1.
Mm-hmm.
And at the bottom you have x2 minus, okay, got it.
Yeah. So I put, so over here, this x goes with that y, a goes with f of a. And that's the other thing, is it's using function notation, which is a little bit harder because I was used to using x and y's. So we've got all these things happening, and when that happens in calculus, and all you see is the h in the bottom, and you can't, it just makes it difficult to understand. But I'm hoping that by spending this a little extra time and letting you say that difference quotient, that difference formula, that's just slope, using a limit to make the value of the distance between the 2 points go down to 0, so that we get the slope at a point. Okay, yes, sir.
What do you mean by these are arbitrary?
What's arbitrary is which point you call the first point, which one you call the second point.
So it doesn't really matter.
It doesn't really matter. So yes, I could have called the top one x1, y1, and the bottom x2, y2, and then my formula will look a little different, which one I'm subtracting, but I could do it either way. But I get some people that get hung up, oh no, you got it wrong, it's y1 minus y2. I know my teacher, my last book showed me that one. But I'm just saying we could do it either way. And the negatives work out in the end because we're getting a ratio. So you can say, so that's the arbitrary part, which one we call y1 and y2. Of course, in this one we don't use x1 and y1 anymore. We use a and a plus h to get us those 2 points. So we really just focus on one point, add an arbitrary distance to it, and by arbitrary I just mean that it could be big, it could be small, but it's a variable distance that we'll add to it. And the goal is to make that distance smaller and smaller and smaller. And one of the techniques, we're just going to plug in 0.0001, a really small value, and a lot of times that'll work. Okay, so that's what I kind of like about this section. It really kind of cuts through all the stuff we were doing before. It just says, just plug in 0.001 for h, put it in this formula, and you'll get pretty close to the derivative. Okay. So let's save a picture of that. And every time I do that, remember, I can always go back. It's still there. And there'll be a PDF of that. So, if you want to print those out for notes, or you'll have access to those. Okay, so that's x1, y2. We get that. Let's talk about this, though. If a function has an endpoint, it has a place where it stops. It either has a beginning or an end. Those endpoints, which sometimes we do, sometimes we define a domain that's specific. What happens at those endpoints as far as limits? So let's do this one. I've got one here. Let's say this is my function. I got it. What can I do with those endpoints, and what can't I do at those endpoints?
You can probably find the secant.
Okay, we could find the secant point because we could use an internal point maybe here, And then, yeah, we could find that secant. Good. We can do that.
You could also
Right.
probably find like the highest part and the lowest part of the function.
We could, if we go in time, internal, yeah, highest and lowest. What about limits? Can we take limits in here? Because it's continuous, so we could do it everywhere in there. Do we have any problem getting a limit at the end? Remember when we were taking limits, what do we need for a limit to exist? We need two things.
It can't be equal.
They need to be equal. What two things need to be equal for a limit to exist?
The domains.
And I come from the left and I come from the right. I need to be able to come from the left and the right, and I need both those limits to be equal. And I can do that for just about all those points, but can I do that at the endpoint? This endpoint has a problem. I can come from the, what's this, from the right, but can I come from the left? I can't, there's nothing there. So it only would have a one-sided limit. So that in itself says I can't take the limit because I can't do both sides. The other end has the opposite problem. I can come from the left and get a limit, but I can't come from the right. So the endpoints won't have a derivative. And we'll talk about that later, but you'll see why endpoints, you can't take a derivative at an endpoint. And that's important because if we've got data, sometimes we want to know what's going to happen next, but we got to be careful because if that data is an endpoint, we really, the calculus breaks down at that point, okay? If it doesn't continue on. So it seems like a minor thing now, but again, there is no such thing as a derivative at a point, at an endpoint. And that's because we can't get the limit. Even though we'll start taking derivatives without the use of limits, derivatives are based on needing a limit. Okay. Okay. So that's that. I'm going to show you the two techniques. Talk a little bit about the error, and then let's just start looking at some examples, because what we're doing is stuff hopefully you've already done in the previous homework, but let's look at how it looks a little different. Okay, so there's two numerical approximation techniques. Okay, so where am I? Here we are. Techniques. Is that right? It's a strange looking word. Did I get it spelled right? I know some of you guys are good spellers. My 7th grade annual, did I tell you about my teacher called me her most creative speller? So I'm a very creative speller. Not a bad speller, just a creative speller. But I'll let the rest of you kind of bring me back. Okay. So we've got two techniques. The first one is what I talked about, is when we've got this this different quotient. And we'll go back and we'll put that in. Is when we've got this thing that is the limit as h goes to 0 of this fraction with f of a plus h, and again a is a point that we're going to be given, minus f of a. So we've got two y values in the top, and then this is a combination of the two x values, remember, so it is a slope. When we deal with this, the first technique numerically is just to let h equal 0.0001, plug that in for h, and then do all the mathematics, and you're going to be just fine. You get a pretty good estimation. The second technique, and again, we'll apply that. That's all there is to it. We'll set it up as a slope formula, but we'll use this one, f of a plus h, and we'll see how that works. We'll just plug in 0.001, and that's going to be a good enough estimate for us. Another estimate we can do that actually sometimes works out to be a little bit better, and this is actually what's going on, at least I think it's what's going on, inside your graphing calculator when it finds a derivative for you. The second technique is to, instead of taking the point in one side, because again, where's that h? Is it coming from the h has to come from the left or the right. I guess h could be negative, right? So you're getting sort of a slope on one side or the other. And depending upon how that graph is, it could be, you know, steep on one side and not so steep on the other. So you may have a little bit of an error, or maybe a lot. So the other technique is to say, well, let's split the difference. Let's have 2h. Well, let's take h and let's go h to the right and h to the left. Let's get the secant line of 2 points that are really close to it. And that's called the balanced approach, because it kind of averages out the left side and the right side. So we get a new formula. And again, I'm going to walk through the extra step that they leave out just to show you that it's really 2 points. And I'm going to give myself, actually, let's save this screen, and I'm going to give myself a whole new screen. Okay. So we're going to start off by talking of the derivative. So I'm going to just call this the derivative. And when we talk about a derivative at a point, here's the notation for that. They just put a little mark on top. They call it a prime. So this is called f prime at a, which means the derivative at the point a. So this is not a function value, it's not a y value, it's the point, it's the slope at that point of the tangent line. It's the derivative. This is what we're looking for. So you'll start seeing this notation. And what we're going to do is we're going to do it with 2 points. And I'm going to define one of the points to be a plus h is the x value, f of a plus h to be the y value. So that's one of the points. And then what I'm going to do is instead of using a, I'm going to use a minus h. So I went to the left as well. And the y value, of course, is going to be f of a minus h. Okay. Enough abstractions as there is, but again, the goal is I've got a point A. It's got some function value, and what I'm doing is I'm just picking 2 points, one to the left, one to the right, that are the same distance. And again, we'll make h really, really small. But what this does is if we put these 2 points into our difference formula, what do we get? Well, we get this a value, so we get f of a plus h. And then we subtract the other y value, which is f of a minus h. Now again, remember, this is somewhat arbitrary. I could have had the order, I could have had it the other way around too, as long as I had the bottom the other way around. So if you see it in a book a little bit differently, just look, okay, mathematically it's all this, you know, Little Crow put the plus first, this author decided to put the minus one first, but it'll all work out. What goes in the bottom? Oops, this one, the x value, right? So we put in a plus h here, and then we subtract the other x value, a minus h. And since we're plugging in a point, I'll actually put a parentheses. So this negative is going to distribute, right? It'll make that a negative. What will it do to this minus h?
Positive.
It will make it positive. Very good. But do you see now, this is just a slope formula. But did they show you that in the book? No. This is what they showed you in the book. They write it down. Okay, nothing does happen to the top part, so yes, they rewrite it. F of a plus h minus f of a minus h. So that's not too much of a mystery. You can see that part. But in the bottom, we've got a minus a, which is zero-roni. And then we've got h minus a negative h, which became a plus h. So h plus h gives us 2h. So you see this formula, and you're wondering, where's that 2h? Oh, I guess they just made it up. I don't know. That's what I used to think. But this is the formula we're going to use for that one. So when we want to take a derivative, and again, we really shouldn't say equal. They use these squiggly lines to say approximately. It's close enough. But this is what your calculator uses, so it's pretty darn close. and then just plug in 0.001. And this will give you a little bit better estimation on most functions. Some functions that you won't be able to tell the difference. Again, it just depends on which point you're at. If there's a big difference between the left and the right, this one will give you the best estimate. Okay. These things are good to know because as you're going to be business majors, you're going to have different aspects. You need to remember you're probably going to be relying on a lot of input from a computer. The computer will run the data, spit it out, and you need to know that even computers have limitations. The book talks a little bit about that, but one of the limitations, like for an Excel spreadsheet, you think, well, if I want to get really close, let me just put 0.000, put like 15 or 16 zeros there. And it talks about it, that's called, I wrote it down because I'd never heard it before, it's called a subtractive error, because if you make h really too small, the computers will actually just put it as 0. They lose the ability to tell the difference between the points when you try to numerically go too small. Okay, so just be aware of that, because that might creep in. You might be able to spot patterns that are occurring, and then the engineers come in and say, oh yeah, this is we ran the calculus on it, and this is it, and everyone's going to believe them because they're supposed to be good at math, but they used a computer that had a subtractive error. You might say, no, this data really tells me that we should be going this way. You guys are way off, and you might be able to spot those kind of errors because those things happen. Even with scientists, especially with scientists. Anyone hear about the Hubble Space Telescope? Went up into space. There was a scientist working in Europe, I guess, or an American scientist. They forgot to convert their units. One was dealing with inches, and they didn't convert, so something didn't work. Couple $1 million later, they got it fixed, but it was a conversion error. Simple thing. You would have known, hopefully you would have known to do that, but they forgot to do that. So things like this happen. So again, your goal as a business professional is to watch to understand mathematics to the point where you know that there can be some problems. Okay. Just like you don't have to know how to fix your car, but when you take it into a mechanic and he tells you something like, oh, you got to replace the air in the tires, because that's a $500 job. You go, wait, replace the air in the tires, really? I think they're trying to get some money out of me. So know enough so that you know what sounds right and what isn't. Okay. Okay, so this is the second technique, is we're just going to do this, and then, yeah, we could plug in 0.002. So the calculators will do this. That's kind of the formula they use to find a derivative. And then finally, just a little bit on notation. A little history, I guess. Just the name of Leibniz, that's what I've always pronounced it. Does anyone, I don't remember his first name. From that name itself, though, does anyone know what nationality that person might have been? Lebanese? Could have been. I think it was either German or French. I'm not really sure. I think it was French. Why do I keep losing? Oh, there we go. We came back. But I contrast this with Isaac Newton, which, does anyone know who he was and where he came from? Got an apple drop on his head, right? That guy. He's British or English or whatever. And so there was an English guy. He also had a calculus, and he had a slightly, I think that's where this notation comes from, this prime. It's a little easier to understand. Leibniz, I think he was German, but he might have been French. I'm not that, look it up. I wasn't that interested myself. But Leibniz, he came up with this notation where when he did the derivative, he started with, oops, this one. Where am I? Okay, I'm over here. Leibniz started with thinking of the derivative as the change in the function value divided by the change in x. And that's really what the slope is, or average rate of change. And so what he did is instead of using all this notation up here, he just says, well, this is the limit as the change in x itself goes to 0. So notice they got the change to go to 0 by letting h go to 0. And then he's got this formula here, the change of f over the change in x, let the change of x go to 0. And so you might see this, he wrote it, instead of having all this notation, he writes df over dx whenever we talk about the derivative. You'll see this later in the book, so it's kind of like this little symbol here has all this stuff. It has the slope in it. It has taking the limit of the slope with the change in the x going to 0, and that's how Leibniz wrote it. Okay. Newton wrote it this way. That was the other problem I had, is there was two different notations that you're trying to learn at the same time, and I got comfortable with one, but it was like my teacher always put the other on the test that I wasn't very comfortable with, and it was just, I knew how to take a derivative, but the notation was giving me troubles. Okay. Yes, sir.
So that just means slope. df(f).
Yes, it really is a slope at a point, so it's instantaneous slope. Okay, that's all the derivative is. So that's why we spend this whole first week, 2 weeks, how many? 2 weeks, right? These 2 weeks getting the theory that it works. And again, the goal is that you can understand, okay, not that you're math majors or anything, but you can say, okay, I get it. Now give me the easy way to find a derivative. But I know what we're doing is all calculus is about finding slopes, rates of change, because that slope, it can be predictive of the future. So knowing where we are and knowing what the derivative is could tell us where we're going to be tomorrow or down next week. That's what we use this for in business and in physics. Yes, sir.
So you can pretty much think of a derivative as like a slope for that exact point in time.
Exactly. Exactly. It is the slope at an identical point at a particular time. Yes. And we can't do that with algebra. Algebra, we need 2 points. So that's this whole conception was invented of this limit, so we could let 2 points get so close together that they become 1 point, and then we can talk about a slope at a point at a particular time. And that was revolutionary mathematically. It really opens up the door to doing a lot of things that we can't solve with algebra. That now we have something to solve. It's the mathematics of change. Because by knowing where we are in this very instant, we know where we're going to be in the future. Or at least we can make a good prediction. And I think, there's a lot of philosophies about that. What you're doing right now will tell you where you're going. So, that's why you're in school, right? You're learning because you want to make some change in your life. You want to be able to do something next year that you're not able to do this year, or at least people won't let you do it. You could probably do it, but until you have that piece of paper, right, people don't let you do it. But it's more than that. It's you're preparing yourself to do something more. That's what your actions are doing. We could all be down at the pool hall having a good time. There's nothing wrong with that. But if that's all we did every evening, maybe that's what we'd be doing next year too. And so the time you're investing here in your education is going to take you to the places you want to go. Okay, back to math. Okay, good job though. Okay, so that's really 10.5, and it gives. So we're going to open up the book and take a look at a few problems, how they work, and what they're doing with that, and then we'll look at a few examples with the calculator, how we can do it. Then we'll look at the algebra behind it, which is 10.6. It's going to involve a little bit of factoring when we get to the quadratics. The linear equations are actually fairly easy to do. That's what we'll start with, a few linear ones. And then we'll look at the quadratics, and that's where we end, because anything above a quadratic is just like pretty monstrous to work with. You could do it with a cubic, but it better be very specialized. But we'll see. But by doing the quadratic, we'll see a pattern that works. And then in chapter 11, we start getting these techniques for just taking the derivative directly without using limits anymore. So we thank you guys for giving us limits, but we don't need them once we get on to the next stage. So here. Oops. 2 student view. See, 10.3 and 10.4 are still available. 10.1 and 10.2 have disappeared, but if you need them, just again, I'll take a look. If anyone who hasn't finished, I'll open them up, and then I'm going to move all the due dates to the end of the class, so we don't even have to worry about that. So we're going to take a look first at 10.5, a few of these problems in derivatives, and if I can. I was playing with one, but I don't know if I can. Maybe if you get a problem right, have any of you tried to get a second, another problem like it to practice it a little bit more? Can you do that? Okay, I'm going to have you teach me.
For the last one, it would just count as wrong. The last chapter is 14.
Yeah.
That one. 14.1.
Uh-huh.
Yeah, it will just count it wrong, and you can't redo it again.
We'll have to do something about that. 14.1. So you've already went and tried. Okay. Thank you. I'll take a look at that, because I think that was one I set up myself. So it's probably I did something weird. Yeah. Thank you. Yeah, if there's an error, it was probably me. Well, not probably, it was. Okay. So so maybe after we do this one, you could show me how to, because I couldn't figure out once I got a problem right, it wouldn't let me do it again. I've done it where it was wrong and it would let me do it again. But so what we're doing with these ones is they've actually done all the work. So but what they're asking us to find is the derivative of this function r at -7. Okay, and then what they're giving us is they're not giving us y values, but they're giving us average rate of change. Okay, and then what they're letting h do is it starts at 1 and goes down to 0.1 and 0.01 and 0.001 and 0.0001. So this is coming like from one side, right? This would be, if you're adding 1, so this would start at -6 and then get the, but it's already done the calculations for us. So that's what I think, the few people that asked me about this, it was kind of confusing. They've done all the calculations, but what do you see happening to the slope as h gets smaller, as the distance to the point -7 gets smaller and smaller this way? It gets bigger until it gets, but then it starts getting closer to a particular value. What would you say? It's 8. It looks like 8.5. We come from the other direction, so this is subtracting 1 from 7. So this is starting from -8. So what we've got a point. We're looking at what is the slope at -7. X is -7, but they start out at x is -6, and then on the other side they're starting out at -8, and they're moving both those to be closer to -7 by making the distance. So h is that distance. They make that distance smaller and smaller and smaller, and in both cases it looks like 8.5 would be right in the middle of that sandwich, right? And that's all we're doing with this one is, yeah, 8.5 is the derivative. They did all the heavy lifting for us, but it actually was probably not as helpful as they wanted it to be, because we didn't know what was going on. But explaining it, what they're doing is letting h get down to 0. So in this case, we're just going to say, oh, what are we going to say? What am I?
It's right under the question.
Oh, it's right. I should look over here. It's so light. Okay, thank you. So it's right there. Enter a number. How about 8.5? And again, so you're learning how to read those tables. We'll do this one. They got a couple other ones. but I think you'll be fine with them. Okay, so that's a concept I want you to have down. Okay, this one they actually want you to do all the calculations, and it does get to be a little tedious. I don't know that we'll do all of them, but I'll show you the steps that you really should go, because you're going to need to calculate the slope 3 different times. Okay. Let's go a little darker. So what we're going to do is h is going to go from 1 to 0.1 to 0.01. So the points we're going to end up with, we're trying to get really the derivative at 3, t equal to 3. So we're looking at the point 3, comma what? Well, how do we find the y value for this point? Enter that into the equation. So I'm going to see 30t minus 2t. I'm going to show you how to get actually all 3 values at the same time by using a calculator. And again, this is we'll do this once and it'll help you with all the others. Here we go. Okay, so we're going to put in that function, which is 30x minus 2x squared. Now again, when you go to do this problem, you may have a slightly different problem, but the technique is going to be the same. Okay. What we need, though, is we need to go to the table of values, and we need to get the value at 3 plus 1, at 3 plus 0.1, and at 3 plus 0.01. Okay. So we're going to go to our table set. It's kind of what I showed you before, and we're going to change our independent from auto over to ask. So we arrow down, turn it over to ask, and now we're set. We've got the equation in our y1, nothing else in there. We're going to go second table to take us to the table, and now it's ready for us. We're going to plug in 3, and it gives us the y value. It did all the math for us. And if you're challenged and you want to try to do this just mentally, you're fine to do it. But you're going to do 3 different calculations, and when you get to the 0.1 and the 0.01, it's probably going to be problematic. Okay, then I'm going to put in 3 plus 1. Watch, I think I can do this. 3 plus 1, and it even calculates it for me. So you could do this again. You could have just put in 4 if you wanted to, and then the next one it wants is 3 plus 0.1, and then it wants 3 plus 0.01. Now again, you probably could have just plugged those in, but I want you to see that you can actually, using this table feature, you can actually plug in the value of h, and I think intellectually there's a value in doing that. Yes, it's simple arithmetic, but as you entered it in, you're telling your mind, I'm getting 3 plus a little bit more, and I'm moving that distance down. And these are the values I'm going to use. I'm going to write them down over here, and then we'll come back, but I'll leave that up there. So it's going to be 372 will be the main point we use, and then we're going to use these 3 other points to calculate the slope 3 different times. Let's see, how should I write this? So this for this one is going to be 4,88. This one will be 3.1, comma. Oh, I did this with someone else yesterday because they were on Tuesday because they were ahead, and it actually gave her an error. It said it wasn't correct, and here's the reason. Notice how many decimal places are showing for the y values. 2. When I come over here, oh, there's only 2. But when you highlight it, it'll tell you exactly how many there are. What the problem was is, and maybe it's on the next one. It is. See, that next one's not really 72.18. It's 72.1798. That made the difference between getting the answer right and getting it wrong, believe it or not. So we want to use four decimals of accuracy. This is the thing is because we're getting so close, we need we need as many digits as we can. And if you just copy down from the table, you may get WebAssign to say, nope, that's not right. You're off by a decimal point. And so this is the point. This is the number we want to use. Okay. So just when you use your table, look at the y values, highlight it to see if you're getting enough digits, and use all of them. Okay, so this is 3.1, let's see, and you'll see back when I get here. This is 73.78, and then the last one is 3.01, comma, 72.1798. Okay, so now I'm going to switch back to the computer screen, and you'll see I wrote those numbers down right above the place where the slope is going to get calculated. Okay, and so you need to use these. And again, the problem we had yesterday, and I couldn't figure it out, but she was only using 2 decimal places, so she 0.18, and it was counting it wrong. And we did it, and then we got, I mean, it was like 1 digit off, but this is what we need to do. Okay, so then your job now is to take these secondary points and the first point, calculate the slope, and that's what goes here. Calculate the slope between these, that's what goes here. Calculate the slope between these two, that's what goes there. Okay, and so I've got it set up for you, and again, we'll leave it at that for now. If you need some help with it, we'll go through it. But this is really what we were doing in 10.4, finding average rate of change, but we do it 3 times. Okay? Not too bad. Okay. And the other thing they throw in here is then when you get the average rate of change, you also have to tell what the slope is. So you have to read the problem, and hopefully if you read this, it's the value of an ounce of palladium in US dollars as a function of the days. So T is days, Y is dollars. Remember, Y is always in the top, so it's going to be dollars per day as a function of the time in days. Okay, so you just have to get that one from reading the question. Remember, you get 3 tries at it, but it's letting you know that every time we get a derivative, it is a rate. A rate is always a fraction, and the units of that rate are important to us, especially in business. Okay, this is not dollars per year, this is dollars per day. It's not dollars per month or week, so it gets us, we have to know these things, because it's a big difference. Right? Questions? Yes, sir.
Why don't you plug the like the 4 into and the 3.1 and 3.01? Where do you plug those into?
Where do we plug them into? So what we do next is then we find the slope between this point and this point.
Well, I mean, how did you get?
How did I get the 4?
No, the 88.
Oh, I was using the same function. So this, remember, I did my calculator, so it was using this function.
So you did 30 times 4.
30, yeah, the calculator did. I was too lazy to do anything. So the calculator, yes, this calculator took 30 times 4, and then it subtracted 2 times 4 squared, and it got a result. So what I'm trying to, yeah, we're going to get that function. So as we do this with calculus, it's the thing is there's so much going on. If you try to do all the calculations, especially as we get more funky stuff going on, it can throw you down. But that's, yeah, each of those x values was plugged into the function to get the y value.
Okay. So why are we adding h to x?
We're adding h to x because that's our second point. So x is 3, it gives us 1 point. We add a distance to get a second point. We let that distance become smaller and smaller so we can see what is happening as we get close to that point. because we don't have the, and what this is going to do is it's going to convince us that taking the limit, that it does give us a value that is what we can now rely on as the slope.
Right, but what is h defined as?
The distance from x.
Oh, okay.
Yeah, so h is the distance from x. And in this case, it's a positive distance, so we're adding it. If it's a negative, we could be subtracting it. We'd be on the left side. Okay, so this is all we're doing is the limits. We're sneaking up to that point from one of the sides until we get closer and closer. And we're seeing, yes, the number gets closer and closer to something. And then we can say, yeah, that's close enough. Yes, sir.
So is the answer not 72? Since it's asking for 3, like when you put 3 in and you get 72?
72 is the function value. It's the y value. What it's asking for is what is the derivative at that point. So what is the slope at that point, which is going to be something completely different. Because what you're going to see, let's do this last one maybe and see how we could probably, this is going to be the most important one. Would you agree? The closer we get to the value, it's going to be the more important one. So let's just do that one. So I'm going to take, let's see, where am I? Here we are. So I'm going to take this point. I'm going to subtract 3 and 72. Okay, so I'm taking that point from the top. When we subtract these, would you agree that 3.01 minus 3 is going to give us, in the bottom, 0.01, right? That's that. This is the change in x. The change in y, 72 point all this stuff, minus 72, is going to give us 0.1798. So if I take 0.1798 divided by 0.01, this should give me the slope of that secant point, but those points are now so close together, they're only a distance of 0.01. It's going to be close enough to estimate the slope. So let me put that in there and I'll... What was it? It was, it's clear. It was 0.1798 divided by 0.01. And you'll see the rest of the stuff that we did. So it's, well, I could have done my head, but oh well.
So 18?
I would say 18. Yeah, it's getting closer to, because we're not there yet. But if we went maybe 0.001, we'd probably, I would guess that one as 18. Good. So as we come back to the main screen, computer screen, what we put in here is our value that we actually got, which was 17.98. But when they want us to estimate the instantaneous rate, I would go with the 18, right? That's, yeah, so they're wanting us to take that leap of faith that we're getting closer to 18. That's got to be the slope at that point. We're missing the other two, but they would have probably slowly gotten us closer to 18. They probably wouldn't have been 18. I'll let you do those. Let's see if we got this right. We got the 2-part that we answered. The other 2, you'll just have to work on. But this is the one because, again, remember we rounded this to 0.18, so she had 18 in here. Or actually, the problem's a little different, but it was marking this one wrong because we didn't use enough of the decimals. So that's what I wanted to prepare you for, is use all the decimals, because I don't want you going home at 2 in the morning getting a text message that might make me up and say, you know, what's going on. So you, no, I don't mind getting, I turn my phone off at night, so if I'm sleeping, I'm fine. If I'm up, I might turn it on, but, okay? So does that make sense? We're just taking the slopes. And the most important slope to get is that last one, really, but they're having us do the other ones to give us that sort of the scaffolding so that we become believers that this actually does work. And we work a number of problems this way, but it is tedious, but hopefully we don't have you do too many, at least not by my estimate. Of course, teachers always say that, right? Because so far, so good? So if you got that part down, you're really good to go. So let's do that one. Save that. Another problem, a slightly different equation, same thing. That's why using the calculator will help you through the calculation parts. It's going to be tedious. There's a number of calculations, so use the technology where you can to do this. But you're going to plug in 2 for x, get that y value, and then you're going to get 3 other points, and then you're going to calc the slope of those 3 other points, and hopefully, if you do it all right, they're going to be getting closer to a particular value, and that's what's going to be the derivative. Okay, so again, technically a little different, but pretty much the same. So now it looks like we're into the part that deals with graphs. Okay, and when they're giving you these values, what they do is with the graph, they give you pretty much one graph, but instead of putting numbers here, they tell you up here so that they can change these. These things that are in red can randomly be changed by the program. And so if so that your question is a little different than your neighbor's, maybe different than mine, and that if you don't get it right, you can ask for another one that the problem will be a little different. So they're telling us A is 3 and B is 6. So that tells us that each of these tick marks is 3 units. And the same thing here. This would be 3, this would be 6. So now they want us to find the... they're telling us that this red line is a tangent line. That's important. So what is a tangent line? What's that? Touching how many points on the graph? 1. It's actually, I don't know how it does it, but a tangent line only touches 1 point on the graph. Now, I see the second point. It's actually touching the second one, but it's at the point of tangency. I should say that. The point of tangency only touches 1.
That's the point of tangency. Is that like just where?
It's you just put a line in there, and when you finally get it, so it only touches 1 point, that's tangent. It's sort of a circular definition. How can you really find it? It's the line that will only touch 1 point. And if you go a little bit one way, you'll end up touching 2 points. If you go back the other way, you end up touching 2 points. So there's only one line of tangency. And what we're going to find out, so this is all theory sort of stuff, but that's what the derivative is. It's the slope of a tangent line. And the only way we can do this is conceptually, is that, we can take these 2 points, which is a secant line, and if we get them to touch each other, the 2 points become 1. That's the tangent. Okay, so it's conceptually, but physically how we do it, it's a toss-up, because we sort of eyeball it. But this, if they're giving it to us, though, we know this is the tangent, so it's going through that 1 point that we want it to go through, right? What point is it going through? It's going through an x value of 6. Okay, so I think my thing here is blocking it. So what we want to find is the derivative at that particular point. Now maybe it's not exactly 6, but whatever it is, the slope, this tangent line, what we can do, the way we have to do this is look at this line, find 2 points on the line, and again, any 2 points. They don't have to be close together because this line, this slope, is the derivative. So I see a point there. What do you say that this point would be?
6 over 3.
Oh, remember, it's a point. It's a coordinate point.
3, 6.
3, 6. Good. So it's not a slope yet. We need a second point on that same red line to be able to calculate a slope. So do you see another place where that red line looks like it crosses the hatchet?
6, 12.
6, 12. And I think those are 2 good points to use. I guess we could also use 0, 0 if I would have been smarter, but maybe we'll do that, right? But I'll just pretend I didn't see that. But if you saw the 0, 0, it looks like it goes right through 0, 0, right? We could do that. We could check it. But again, we're just finding slopes, so we subtract 1 point from the other. 3 minus 6, negative 3. 6 minus 12, negative 6. Take the x, tuck it underneath the y. So negative is going to make a positive. 6 divided by 3 is 2. If we would have used 0, it would have been 3 comma 6 and 0, 0. The math would have been a little bit easier, but we would have ended up with 3, 6. Put the 3 underneath. We also would have ended up with 2. Okay? So just find 2 good points on a tangent line. We can get the slope, and that will be the derivative. That's what these next few problems are about. Everyone believe me? Please say no. You should never believe somebody, blindly at least. But we'll believe the computer, right? Because it'll be right. Yes, sir.
Where'd you get 3, 6, and 6, 12 on the graph?
Okay, so we have to look for a point where I'm looking on this red line. And yeah, we're good there. So on this red line, I'm looking for where does it cross, I guess, these grid marks. So where it has a nice integer value point. So I see one crossing here, which is 3, 6. And then I saw a crossing up here, which is 6. And this point up here is 6, 7, or it goes by 3, so 6, 9, 12. Okay, so that's the counting. But again, if you're smarter than me, you would have said, oh, there's also this point here. It goes right through that. So I'm looking where it goes right through one of the corner points, because those are nice, easy ones to deal with. And I don't have to make an estimation or something. Okay? So far, so good. So you'll be doing some of these problems. I think there's another one of these. Let me take a picture of this by saving it, and then we move forward. And then the same thing, you know, pick 2 points off of here, find the slope, and you'll have it. Okay. This is one I've already done, but what you've got to do here is just kind of like finding the slope. What you're doing is you're just imagining a line that would go through each of those points. So what I would do is what we're sort of doing is, okay, this point P, its tangent line should probably go, you know, I didn't go through, go something like that. The Q one will go something like that, and the R one is going to go something like this. Which line is steeper? The point that goes through P, Q, or R? You see R, yeah, it just keeps getting steeper because it's going up. So that's going to have the greatest, and the one that's the least steep would be P. Okay, so that's just kind of just getting adjusted, and it's just sort of an estimation on kind of getting as good of a tangent line as we can. You're just eyeballing it through, trying to go just through that point and let the other points around you kind of suggest.
Did you go for 5?
5?
Yeah.
No, I skipped it. So it was probably something I should have, right? Let's see. Oh, no, yeah. Let's see. Let me save this one first. Okay, 5. Pick off 2 points.
Oh, it's the same as.
Yeah.
I just got thrown off.
Yeah, it's horizontal.
Yeah.
Yeah, so you're going to get any of these 2 points. You could pick those 2. You could pick, yeah. You'll see, I think you'll see pretty quickly this will be a 0 slope because it's horizontal. And the y's are not changing. So we got a 0 on the top. We don't have a 0 on the bottom. So it's a 0 slope. And that's what we're going to see is that's how we find maximum and minimums. Is when we have a 0 slope, that means we are at a maximum. So again, in a business setting, if you've got data and all of a sudden you got the calculation of a slope and you know today our slope, our rate of change of sales is 0, whoa, we're at a max. We're either at a maximum or a minimum. If we're at a minimum, that's good because that means that maybe tomorrow's going to be better, right? But if we're at a maximum, it means the sales will probably be heading back down. So we use this kind of information to know, whether to make more stuff or whether to, cut back our supplies, all of these kind of things. Okay. Good. that one I'll just clear. Yeah, I'll go with that. Okay. So we're an hour into this. I think we're, and I'll basically the rest of it I think you'll be okay with. This one you'll have to answer some questions, so you're picking out a point and another point, and you're just kind of imagining some secant lines and answering some questions on it. And that's pretty much the end of this activity. So we did some numerical ones, we calculated a few of them, we did a few graphical, and then what we're going to do is we're just going to use these things that we talked about. We're going to jump into algebraically doing things, and what we're going to do is we're just going to start with some examples. Okay, if that's okay. So I'm going to go, where am I? Oh, I was going to ask somebody, so I got this one right. If I wanted to do a different problem, what do I do? Practice it. Gives me this though. But oh, so does this is an interactive way to, but will it pull up a new problem? It just gives me this. Is that all is it going to give me? It's, okay, there's no way, because I think if I got it wrong, I could ask it to give me a similar problem. Is that right?
Maybe if you do need help.
Yeah, I try. If it's wrong, it'll give you a new one, and I guess if it's right, it says, why would you want to do it again? I guess maybe that's what it's. You should have. I would invent one with a little bit of attitude, and it's going. Why you wanted to do this? You got it right. Okay, so but if you want to do another one, hit the practice. That way it doesn't take any points away if you get the practice wrong. I think that must be it. Okay. But let's see. These I got wrong, so how do I, oh, I've got to submit it 3 times. Let's see, let's just do this. Because maybe someone who's online also, let's submit it. We still got the wrong ones. We did it 3 times. Doesn't it tell you the answers after the 3rd time?
You have to put a different answer.
Oh, so
So you have to try.
you have to try. Oh, no. So we'll do that. Okay. Got those wrong. And then we'll do a 2.1. So that's, you have to do 3.
Just one.
Oh, I could change. Okay. We'll just do that one. So it sees it as different. Another try. And now it will give me some help. It tells me what's right. And now how do I get a new problem? Do I click here?
You go down.
I go down?
Yeah.
Oh, new randomization. Okay. That's what I was hoping. Even if I got it right, I'd like to maybe practice some of these later and have it do that. But I guess it doesn't. Maybe there's a... I'll see if there's a setting. But yeah, new randomization. So if you get it wrong, now we got a new one. And notice it changed changed our formula a little bit. And if you want to practice, go to the practice it. Okay. Water and dry. Okay. So for 6, we're going to do the same stuff, but we're going to do it algebraically. We're going to use this concept of limits. And remember, that algebraic formula we had has h in the bottom, so we can't just let h go to the bottom. But the trick is our algebra is going to get that h to cancel out of the bottom. Then we can let h go to 0, and we can calculate the slope algebraically. Okay, this only works in a limited number of problems, and that's why we have these other techniques. But it will help us understand the techniques that get this to work. Okay, so now we're going to jump over to 10.6, and my goal is to be done within a half hour, because all we got to do is work. We've got the formulas already. We're just going to work a few examples together, and then I want you working a few. There's only 5, so there's not much. I can't work them all, or I shouldn't work them all. So should we start with an easy one and then go to the hardest one? How about if we do that, just 2 of them? Actually, none of them are all that hard, but would you say that, yeah, none of them are really, This one a good one to start with? Okay, so let's start with this one. And what I'm going to do is I'm going to just copy it down, take the function, and give myself some open screen to work with. So it's negative 7x plus 3. We want to find the slope at, we want to find the derivative at negative 6. Okay, I'm going to shrink that down. Let's just use this. So let me see if I get this right. F of x was equal to negative 7x. Oh shoot, what was that? Plus, is anyone paying attention? More? Plus 3. Paying more attention than I was. Okay. Actually, I was paying attention, but it's always the second thing I forget to remember. Okay. So our function is 7x plus 3. And they said, what was it? A equals 6? Negative 6. Okay. And our goal is to find the derivative at a, or just the derivative at negative 6. Okay. Did it? Maybe I better pull it up one more time. Compute this algebraically for given. Okay, so it doesn't say which one to use, but oops. What we'll do is we'll use the difference formula. So we'll go with the limit as h goes to 0 of f a plus h minus f of a all over h. And remember that h is not just h, it was, what was it? It was a plus h minus a, and the a's canceled out. So this was the slope, but now it's a little bit simplified for us. So what do we plug in where? Okay, so we know that a is negative 6, so wherever we see an a, we're going to put in negative 6. And wherever we see an h, we're just going to put an h. So this is where algebraically it gets a little bit hard. So we need to find, so let's see, our 2 points are going to be, well, let's find the first one. So we've got negative 6, plug in negative 6 for x, negative 7 times negative 6, positive 42 plus 3, 45. Okay, not too bad. The second point is going to be negative 6 plus h. And again, you could, if we were doing this numerically, we would just plug in 0.0001 for h, but we're doing it algebraically, so that's what we have to plug in. So now, what is the function going to be? It's going to be, this is some scratch area over here. It's going to be negative 7 times negative 6 plus h, all plus 3. So I distribute the negative 7. I get positive 42 minus 7h plus 3. Is that okay so far? Miss anything? Okay. Combine the like terms, so 42 plus 3, 45 minus 7h. So that's the second point. That's this point here. Yes.
The f of a plus h, is that the negative 7x plus 3 others? Is that
Yes.
what?
Yes. So we're using this function here. So there's the negative 7. This is the negative 6 plus h getting plugged into it. So this is the y value. And again, we don't actually even use these x values because, again, the negative 6 minus the 6, that would have canceled out. So they take care of the bottom for us. That's why just leaving that h there is fine. If you want to take that extra step, and that's how I sort of learned it, you could actually just take the slope with these 2 points. But these bottom ones are just, the bottom's just going to be h. So then we're left with the limit as h goes to 0 in f of a plus h, that's this, 45 minus 7h. And then we're going to subtract f of a. That's this value here. That's this y value, 45. So minus 45. In the bottom, we just have the h. And again, you could see if you subtracted these two x values, that's all that's left is h. Maybe a negative h, but anyway, the way it's done, it's fine. So, using our algebra skills, what does the top part simplify to? Minus 7h. Because 45 minus 45 is 0. We still have the h in the bottom. We've got the limit as h goes to 0. And now using our extraordinary algebra skills, what is h divided by h? It is 1. So we can cancel those out. And when we do that, we get the limit as h goes to 0 of what? Negative 7. Can we let h go to 0 now? Sure, it's gone. It's no problem. It's like it's left the house. Who cares? It's not in the denominator anymore. It can't. That's the trick. Is we cancel it out of the denominator. We go ahead and let it go to 0. So then we don't even actually take the limit anymore because we've got. Remember, this is all this theory. We've got a continuous function. It's actually a constant function, and so we can actually go ahead and just algebraically take this limit and say it's equal to negative 7. So what we can say is the derivative at the point negative 6, algebraically, we found we're not even using limits anymore. We sort of got it to get there. It's negative 7. Yes?
Can you, like, literally, just looking at the problem, see that one, like, out of the two numbers, one's paired with x, and that you can kind of just, like, immediately off the bat know that it's going to be negative 7 because you just take away the x, and then the 3 doesn't have anything to do with it.
You're getting into next week. But
Next week,
let me show you, since you raised the question, that's exactly what we're going to do next week. A little bit more elegantly, with a little bit more math stuff, but exactly what you said. This is the way we'll end up taking a derivative. Let me change colors because this is a preview of the future. So you're right. Oops, yeah, 7x. Let's do a lighter blue. Shows up better. So we're going to have negative 7x to the first power plus 3. Next week we're going to find out is that we can actually take polynomials, we take them term by term. We can take the derivative. We'll learn that the derivative of a constant is 0, horizontal, right? So when we have a constant, that's going to be 0. When we have a power of x, x to the first, x to the second, what we do, this is what I mean, it's going to seem so easy. It's exactly what you described, and I'm glad you saw that pattern. That negative 7 is because there's a negative 7 in front. What happens is this exponent comes down and gets multiplied by the coefficient. So negative 7 times 1 in this case. And then we subtract 1 from the exponent. Remember I started the first day and asked how many of you guys could take 1 minus 1? This is why. That's all you. 1 minus 1 is 0. X to the 0 is 1. So what we end up with in this whole process is negative 7 times 1, which is negative 7. That's how we're going to take the derivative next week. And you'll see with the square, the 2 comes down, so you'll see that the coefficient gets multiplied by 2, and then it becomes x to the first power. That becomes our derivative. X to the third power, the 3 comes down, multiplies. 3 minus 1 is 2. We got x squared. So you're going to, yeah, exactly. And that's the patterns. That's, as we spot them, we say, okay, this is what could do. But algebraically, this is painful to do each time, right? Especially when you say, oh, negative 7, that's the slope. Oof, yes, we'll get that. It'll be that quick. Good. So that all that's really left to do is to show you what happens when we have a quadratic, because quadratics are algebraically more difficult to deal with. But remember, there's only 2 in the problem sets that are quadratic. So let me save this one. And we're going to put that -7 in just to make sure it works. And then we're going to be done with tonight's lesson. And you'll have plenty of time to work through the problems. So let's just put that -7 in there. And then we submit it. Where are we? Here we go. Yeah, it's right. Okay. So then now let's take this quadratic. Again, we could do this one. We could do this one. Oh, maybe this one. This one is going to be the most challenging one because it's got 2 x's. And your problem may be different. Instead of having a 6, it'll have something different. But from what I just showed you, can you estimate what's the derivative going to be? Let's do that here. So what do I do with this exponent? I multiply. So that's going to be 6 times 2 is 12. I subtract 1 from it. So that's going to be x to the first power. The second x is x to the first power. So the 1 comes down, multiplies, and then 1 minus 1 is 0. So x to the 0 power. So my derivative should be 12x plus 1. Does that make sense? And we'll go back and do this algebraically because this is what we're going to learn next week. So what would be the derivative at 6? So this is not the function, this is the derivative function. So we've got the derivative is actually a function because it actually changes along this parabola. What's the derivative at 6? 73. 6 times 12 plus 1. So the derivative at 6, plug it in, you'll see it's 73. We're going to do it all algebraically, but that's what we're going to need to end up with. Okay, and you're going to be thinking, dang, this algebraic stuff is a pain. It is. Some of you will be better at it than others, but we'll just walk through it. Just remember, just try to do your best to kind of get through it, because that's you kind of got. We could just put 73 and be done, right? We don't have to show our work, but I want you to be able to understand the work for this. Okay, so we'll clear that off. 6x squared plus x. Shrink this down. So what do we have? We've got the function of x is, what was it, 6x squared plus x, and this one wanted to find the derivative when a is equal to, it was positive 6, wasn't it? Okay, so let's walk through this using the difference quotient, the slope formula. And this is, again, just rewriting it. F of a plus h minus f of a divided all by h. Okay, so we start off, we want to find what is the y value when a is 6. So 6 gets plugged in here. 6 squared is 36. 36 times 6 is a big number. 36 times 300 and something. What's that? 216 plus another 6, right? That must be 222. Did I get that right? So you plug the 6 into this formula, and I would do it with the calculator, which I'll do right now. Plus 6. Plus 6. Yeah, so we're going to put in x squared plus x. Actually, let me, so I put it, oops, forgot the plus. Okay, so we put that in. We go to our table, and we've got it set up for ask. So if I just put in a 6, it's 222. Okay, so we'll just clear these out. We don't need this is left over. But so I encourage you to kind of get used to doing that. Put the function in y1, and then use your tables to find your values. Just because this is tedious, and if you get the wrong value and you're working with wrong values, you get the wrong answer, where you might have actually the right concepts. So, and we won't do this too much more. Actually, it's the end of the line. From here on out, we don't deal with the theory part anymore. We deal with the easier ways. So then we've got 6 plus h here, and when you plug in 6 plus h, again, this is where the algebra gets messy. So what are we going to have? We're going to have 6 x squared, x in this case is 6 plus h, plus 6 plus h. So you can see how quadratics just get to be messy to deal with. Okay, 6 plus h squared. Anyone good at squaring binomials? I think what that should be like 36 plus 12h plus h squared. And again, if you haven't had a lot of practice with these, you might just take it as 6 plus h times 6 plus h. Foil it out. You'll see you should get 36 plus 12h plus h squared. Questions on that? Okay. We can work on these individually as well. Okay. And then we've got plus 6 plus h. And now the 6 distributes through. So we just did 6 times 36 is 216. 6 times 12 is 72. And 6 times 1 is 6. So plus 6h squared plus 6h, or 6 plus h. Combining like terms, let's see, we've got an h here and an h there, a 216 and a 6, so we end up with 222 plus 73h plus 6h squared. Didn't put anyone to sleep, so that's good. Did I lose anybody? Okay, good. So just kind of, again, don't get too blown away. We won't be doing too much of this. So that's the y value. And so that goes, I'm not going to rewrite it all. That's the y coordinate here, and that's what goes in for f of a plus h. Okay, so I'm going to rewrite our limit formula with what we just did. So this whole messy thing goes in for f of a plus h. So it's 22 plus 73h plus 6h squared. Then we subtract f of a. f of 6 is 222. Notice how this is always going to work out kind of nice, that we've got some canceling going on. Okay, the 6 part goes out. And then that's all over h. And again, remember this x part, the 6 is what have canceled out. We're only left with h. Okay, 222 minus 222, that's gone. So what are we left with? The limit as h goes to 0. We've got 73h plus 6h squared over h. Can we let h go to 0 now?
Yeah.
Why? Is there any danger in letting h go to 0? Mathematical danger. If we have a 0 in the bottom of a fraction, what's going to happen? It's undefined. So the, oh, I've been doing all of that. You guys haven't seen anything, right? Someone tell me, hey, little crow, why don't you let us see what you're talking about? Okay, sorry. Oh, shoot, that was. Look what I was doing while it was all blank. Okay. Not only you guys, those people at home, they've been hearing me say this, but they didn't see what I was doing. Because from whenever I went to the computer or the calculator. Okay, so, sorry about that. So of course, yeah, you couldn't see it. So we can't let h go to 0 here because it's still in the bottom. But can we do some factoring in the top? Remember this? We did this like, I think we did this on Tuesday. Didn't we have to do a few algebraic ones where we had a factor? There is an h that can come out of both of these, right? So we factor out an h. We're left with 73 plus 6h all over h. And my limit should carry over. Well, I'll go ahead and do that. The limit as h goes to 0. Now what can we do with the h in the top and the h in the bottom? Now we can cancel them. And since there's no h in the bottom now, we can effectively and realistically let h go to 0. So 6 times 0 is 0 plus 73 is 73. And I think that's the answer we came up with when we took it with that little technique. Again, we'll learn that technique more formally and everything on Monday. That's what 11 starts with, is that technique. And it could just start with 6 times 2 is 12, then plug in the 6 for the x, so we get a new formula. Okay. And again, the derivative formula. So this is what we found is that the derivative of this function at the point 6 equals 73. And what we did, and what we'll learn on, not Monday, next Tuesday, is if we take the derivative of this, we take 2 times 6 gave us 12, subtract 1 from the 2, that gives us x to the first, take the 1 time, and it's going to be a plus 1. The exponent becomes 0, so it's 1. So this is the derivative function. And what we got to do is now we just do algebra. We plug in the 6 for x, and that will give us our derivative. A lot less work, which is really nice. Okay. But then what we start doing is then we focus on how to take derivatives of combination of functions when they're multiplying, dividing, a function inside of a function. So this is not going to get boring for us. Ah, darn, right? But it will get more realistic, and we'll be able to get to something that's valuable for us a lot quicker without having to deal with all this theory about limits and 2 points becoming 1 point, because we'll see that these techniques work. And again, it was just that first one you start seeing this pattern of what the answers are. And take a look at that. So you only have 5 ones to do algebraically. What I'm going to work on tomorrow morning is coming up with your practice test for Chapter 10. And let me get some feedback. I was thinking that it should have maybe like 15 questions in it, and they'll come from 10.1 to 10.6, so they'll kind of be equally distributed out. So that's what? That's 6 units, so about 2 questions per unit, and maybe 1 from each of the other ones. Because if I only do 10, then you miss 1, then you're at 90. You know, it's kind of like one of those things. So 15, usually you can still miss a couple. If I give more, you can miss more. But then it's just, yeah, there's sort of a limit. I found that about 15 is good for chapter quizzes. And the final, usually I'll do like about 30 questions, because that gives you even more you can do. But it's, you know, the final is going to be like 2 hours or such. But 15 sound reasonable for the test? And again, remember, it's unlimited time. You get a page of notes, so that'll be in there. Go ahead and do that. And then if you can, over the weekend, check out the practice quiz that's in there. It's called the Unnamed Quiz, because I didn't want to give it a name. And see if, and that'll test your webcam and your whatever you've got set up. and get you 1 point of extra credit, or maybe it's 10. I can't remember. I think it's 1 point. Maybe it's more. Just got to know what the color of the sky is. For chapter 10, good question. My goal, I'll make it along with the practice test, because that's usually what I do. I make a practice test and I make the test basically off the same thing. So once I have the practice test ready, I'll post that. I'll also have the actual test ready, and that will be ready over the weekend. And then I'll give you through next weekend to take it as well. So, but yeah, I'll try to have it up by the weekend. So for those of you who are kind of ready to go, you could take it. I have a password on it because the password on the practice test is Munchkin. I don't know. I was thinking about donuts at the time or something, but so that's, yeah.
Wait, what did you say the test was?
The test will probably be ready this weekend sometime. So you could.
Online.
It's all online, so it's you take it. So then you'll have all of next week and all of next weekend as well. I'll leave it open for like 10 days.
Okay.
And once I post it, I'll let you know if you need to still studying it, because you might need some. I would suggest going through the practice test all the way till you feel confident, and then when you're ready, go ahead and do it.
Can you do like a quiz before that test, or is it just that unnamed quiz that you're saying?
Well, the unnamed quiz is the one that will test your system. So I'll even give you guys, since you're here, and since people are listening, the answer to the quiz. The question is, what color is the sky? And there's 4 answers. One is blue, one is orange, one is black. So well, sometimes it's all of those. And then the last one, it says depends on what time of day it is. And that's the one I marked as the correct one. So if you want to get it right, you agree with me that the sky is not blue, it's not black, it's not orange. It depends on what time of day. So that part is because I didn't want that part to be that's just all that's there. It's more about testing your webcam. Does that work? Is your system going to be able to handle it? And if it doesn't, we'll make some options for those of you. And again, even if you just want to, we can have you taking the testing center. But I'm going to have it open so that you can take it when you want, and give you guys enough time, give you some practice. And then there'll be a paper version of a practice test. And it'll be multiple choice. It'll be just like the test, except slightly different problems. Slightly different numbers and stuff. Good. Okay. Yes, question on this or something else? Okay.
I just don't really understand what you did after you discovered the 222. So pretty early.
Oh, well, because it wasn't up there, right?
Yeah, it wasn't up.
Okay, sorry. So we plugged in the 6 to this function.
Right, and we
We got
got
the
222.
222. Then what I did is I plugged the 6 plus h in for the x here.
Why?
Because 6 plus h is going to be my second point. So we're
Okay.
still working with that. We need 2 points to get a slope.
Okay.
So 6 plus h is my second point. I plug that in to get the y value. So 6 plus h squared. And then 6 plus h here getting plugged in for x.
Okay.
Okay, and then it's algebra of foiling it out, simplifying, and finding out that when I plug in 6 plus h, this is the y value. And then that goes there, minus the 22, and then, okay, yes.
Oh, I just need some help on some stuff online.
Okay, very good. So are we good with this part?
Yeah, I'm just copying it down.
Okay. Let me do this. So yeah, I'll just leave it up there then. And we'll leave the mic open. But if you're online and watching, because there was a few people watching while I was live streaming last time, we're kind of done, but maybe you want to copy things down. I'll have the video, the link up, posted.
When I was doing this homework, I remember that you said piecewise functions are continuous. Is that right?
Well, they have the potential of not being continuous. If they're not continuous, the place they're not going to be continuous at is this point here, the 0. And so what you have to do is check 0 in both of the functions. If it's the same, then the pieces are connected. If it's not, then the pieces are disconnected, and then it's not continuous.
So So when you say you check them into the function, do you mean you plug that in for x?
Yeah, plug that into x for the first one, plug that into x for the second one, and if they give you the same value, then they are then the piecewise action is continuous.
So you have to set them equal to each other, like 0 plus 6 equals 2, 0 minus 2 times 0 minus 7.
Yeah, and if they are equal, then it works. If it's not, then that's a false statement. And then where they're discontinuous at, which this one obviously is, the place it's discontinuous is at x equals 0.
Okay, and then so this one's continuous, and that's because these are equal.
Yes. Plug in 0 here, you get 4. Plug in 0 to the second one, you get 4. 4 equals 4, so it is continuous.
Alright, so if I do this one, it's the same deal.
Yeah, 6 minus 6 is 0. Oh no. So it's not continuous because you plug in 6 up here, you get 0. Plug 6 in the bottom, you get 12. 12 and 0 are not equal. So it's discontinuous. The place it becomes discontinuous is x equals 6.
Okay.
Does that make sense?
Yep.
I just submitted it and it's my Wi-Fi.
Oh,
Yeah, one thing, I for one do know that my laptop, the camera's not working for some reason.
okay.
It's like broken. So I guess it's a bit of proctoring thing.
Okay. We could have you take it through the testing center. I'll see if I can. Why don't you do this? Go through the process of doing it. Let me know what happens, and then just email me. I'll see how many we have. As there's a way to do it. The other way is getting it cheap.
With a connected camera.
Yeah, USB one that's, and it could be a little cheaper because it doesn't have to have very much. I don't think they use much bandwidth, and the resolution's pretty low.
Okay.
And even if you could just borrow one or something, that would make it easier. If not, we can work out something to do through the testing center or something.
Alright, thank you.
At the end of that, you have 73 plus 6h, and that's pretty much this.
Yes. And so then what I did, I talked through it, but I let h go to 0. So let me come back here. Okay. So then this, what we were really left with is the limit as h goes to 0 of 73 plus 6h. And then we use that stuff from section 10.4 where we could say, okay, this is continuous, so we can do this algebraically. So it just becomes 73 plus 6 times 0. We let h become 0, and so our answer becomes 73.
Okay, that makes sense.
Yeah.
Sorry,
Dang, that was the thing that I should have had showing all along. So one day I forgot to switch back to the screen, but
I was trying to follow along, but I got
okay.
kind of lost. I'm not gonna lie.
Yeah, I looked at it. I got lost. I said, "Whoa!" Yeah, sorry about that. So I'll go ahead and
So it's always